In this problem, we're gonna graph several rational functions. So rational functions are the quotient of two polynomials. So we can see that there are three rational functions, and we can look at the shape of the graph. So when you do rational functions, so we're gonna follow like several basic steps. Um, so as the first one, we normally factor. So that is the major step because we need those factors to find solutions. So we're gonna factor. And the second one is we're going to find the domain. Uh, as the third step, we're going to find intercepts. And then we're going to find asymptotes. So this is one of the major steps in when graphing rational functions because there are no asymptotes for polynomials, but there are asymptotes for rational functions. And then we also have one extra step. What we're going to do, we're going to know whether the graph gonna cross the asymptote, the horizontal asymptote. So we're gonna check whether the graph crosses the um, horizontal asymptote. So that's horizontal or oblique asymptote. It's never crossed the vertical asymptote, but it can cross. Okay, so and then in addition, we can find few more points. Um, and then we can graph. So those are the steps. Find a few additional points and then graph. So these are kind of common steps when graphing a rational function. So let's look at the first one. So we have y equal 2x squared plus 7x minus 4 divided by x squared minus x minus 2. So as the first step, what we're going to do, we're going to find the factors. So for the top, we have 2 times -4, which is -8. So we need two numbers. That's gonna when you multiply, you get -8, and add, you get 7. Those two numbers are 8 and -1. And then using those two numbers, we can write the factorization. And you can see for the top, it has to be 2x and x. And then find the number. You can divide 2. You can divide 8 by 2. So that means plus 4 gonna go there. That's 8 divided by 2. And then -1 divided by 1. That means -1 gonna go to the other one. So those are the two numbers. And then for the bottom, that's the easy one. So you can see the two numbers are -2 and 1. So that means x minus 2 and x plus 1. Okay, so that's the factorization. And then so again, so that's the first step when you do a problem like that. So a factor, so that part is done. Then we're going to find the domain. So the domain is coming from the denominator. So which is we're going to find the two, we're going to find zeros. In this case, there are two zeros. So one is x, which is not equal to 2 because otherwise you divide by 0. And then here it says that x cannot be -1. So that means the domain is simply x such that x not equal to -1 and x not equal to s not equal to 2. So that is the domain. And then we're going to find the intercepts. We're going to start with the y-intercept. So the y-intercept is plug in x equals 0. If you plug in x equals 0 for the top and bottom, you're going to get y equal -4 over -2, which is 2. So that's the y-intercept. And we also find the x-intercept. So if it is in the simplified form, the numerator is going to give you the x-intercept. So that means we're going to set simply 2x minus 1 and x plus 4 equal to 0 to find the intercept. And you can see the first one give you x equal 1/2, and then the second one give you x equal -4. So those are the x-intercepts or the zeros. So these are simply the zeros or the x-intercepts. Good. And then so that's the intercept. And then we're going to do asymptotes. So we're going to go with the vertical asymptote first. So vertical asymptote means if you do look at the simplified form, so this is already we have the simplified form. So this is the simplified form because there are no common factors. And then the denominator is going to give you the vertical asymptote. That means in this case there's two factors, so that means x equal 2 and x equal -1 vertical asymptotes, because you can see that close to those two values the function goes to infinities. So that's what the vertical asymptote means. And after we get the vertical asymptote, we can do the sign diagram. That's the next step. So so we have zeros. So what we can do, we're going to put zeros and asymptotes here. So you can see so there's -4, that's one number, that's 1 0. You put zeros and asymptotes. So so we're going to put zeros and asymptote. So that's what we're going to put it here, zeros and asymptotes. So that means -4. And then we have -1 as an asymptote, and then 1/2 as a 0, and then 2 as a asymptote. So those are the ones we're going to put it here, zeros and asymptotes, both zeros and asymptote. Now we just try to do the sign diagram. So yeah, so this is actually the sign diagram. So let's write it. Sign diagram. So we're going to pick test points as we normally try to solve inequality problems. So we're going to pick t equal 3. So if you pick t equal 3, you can see you're going to plug in t equal 3 in the factored version. So you're going to get first one is 5, so positive, and then 7, which is positive. You just need whether positive or negative, and then positive. And then also we can plug in 3, so 4 is positive. So 4 positive, that means positive. And then we can plug in t equal 1. So you can plug in some easy numbers. If you plug in t equal 1, you get positive, positive, and then negative and positive. So 1 negative, that means negative. And then we're going to put t equal 0 is a good number. And then if you plug in t equal 0 is negative, positive, and then negative, and then positive, and then so 2 negative, which is positive, and then we're going to put t equal -2, so which is so you're going to get a negative, and then positive, and then negative, and negative, so 3 negative, which is negative. So we only need to find the sign close to vertical asymptotes and between zeros. So between zeros and vertical asymptotes. Between zeros and vertical asymptotes only. So we don't need to find a value here because that's just a 0, so we don't. Okay, so after we get that, then we can also mark the vertical asymptote. So there's a vertical asymptote at -1, and there was a vertical asymptote at 2. Now what we can do, we can check how it is moving. So that's the whole point here. So and you can see that more than 2, you can see is positive. That means the graph gonna go like that. Yeah, so graph gonna go like that. That's the idea. So it's gonna go to infinity, but it's gonna go to positive infinity. And then it's a negative, so that graph gonna go like this. And then again positive infinity, graph gonna go like that, and negative infinity, graph gonna go like that. So that's the idea. So that is how you're gonna find those asymptotes. So that's the whole point of drawing the sign diagram. Okay, now we're gonna go to find the horizontal asymptote. So so next step is the horizontal asymptote. So for that, we're gonna notice that the n equal m equal 2 for this problem. So that means since they are equal, there is a horizontal asymptote. So there is a horizontal asymptote, and then which is simply given by the ratio of the leading coefficient, so which is an over bm, so which is 2 over 1, which is 2. So and then so there are no oblique asymptote in this case. So now we have all the information. So we have one last thing. We want to check whether the graph gonna cross the horizontal asymptote, because there's a possibility that can happen. So let's check. So we're gonna check if the graph, check if the graph crosses the horizontal asymptote. For that, what we're gonna do, we're gonna set the function equal to the asymptote value. So that means 2x squared plus 7x minus 4 divided by x squared minus x minus 2 equal to, so 2 is coming from here, you can see, because that's the whole asymptote value. Now we're going to solve this. So we're going to cross multiply. Once you cross multiply, you can write this one as 2x squared plus 7x minus 4 equal 2 times x squared minus x minus 2, so which is 2x squared minus 2x minus 4. And then you can see that x squared and x squared you can cancel, and then once you cancel, you can bring negative 2x to the left side, so you're going to get 9x, and then equal, so you can also see that negative 4 and negative 4 also cancel, so which is 0. So that means x equals 0. So at x equals 0, the graph gonna crosses the horizontal asymptote. So, and then we can see that for x equals 0, it is simply y equal 2, because this is the intercept, the y-intercept. That's like a interest distribution. So that means at the point 0, 2, x and y value, the graph crosses the horizontal asymptote. Okay, so we can use all this information now to graph the rational function. So we're going to start putting the zeros and the asymptote, and then we're going to look at the shape of the graph using those arrows. Then we can finally graph the function. So let's see how we can get the graph now. So we're going to start putting the axis. So we have the x-axis, and then we also have the y-axis. So I slightly move it to the right, because you can see there are more data on the other side. And then we have, so it's better to graph this using a scale, because otherwise these rational functions gonna look weird. So we have 0, and then we also have 1 and 2. So we can say 2. And then also we have negative 1, negative 2, negative 3, and negative 4. Okay, so we're going to put all those special values that we know. So we know that at 1/2, that is one of the intercept. And then also negative 4, at negative 4, this is negative 2, this is negative 4. At negative 4 is also another 0. So we're going to mark those two zeros. And then let's mark this vertical asymptote. So we mark the zeros. Now we mark the vertical asymptote. So there's a vertical asymptote at 2. So that's one of the vertical asymptote. And also there's a vertical asymptote at negative 1. So there's another one at negative 1. We normally draw them as the dash line or dotted line, because they are not really real lines there. Okay, so this is the value is negative 1. Okay, and then also the horizontal asymptote. So the horizontal asymptote at 2, so we're gonna mark that around 2. So this is y equal 2. So this line is x equal 2. This line is x equal negative 1. Okay, so we have all the horizontal asymptote and the vertical asymptote. And then we also have another point. We know that the graph gonna crosses the horizontal asymptote at 2. So we have this value, which is 2. Okay, so we have all the information. Now what we're gonna do is we're gonna graph the function using those behaviors. So first one is, we know that it is at 2, so the graph gonna go like that, and so it's going to go like this for the rest, because we know that the that part doesn't cross the horizontal asymptote, so it has to be up there like that. Okay, and then we also know that our graph gonna go to infinity at this corner, so that means gonna go like that, gonna pass through this and go through 0 and then go to infinity. So I'm gonna go like that. So that's the 0 over there, and this the other 0 over there, and then at this corner, so you can see that the graph gonna go to infinity and then pass through the 0. So it's gonna go like this. Good. So this is not a straight line, this is like kind of curvy, but we cannot see it because we need more like large axis to see it. Okay, so that's the graph, and then this is the x-axis and the y-axis. So you can see all the information that we had to zeros and the behavior near asymptotes help you to graph the function. Okay, now let's see, like if you use a there are some available graphers, like graphing calculators, so you can see what kind of graph you're gonna get. So this is what you get if you use one of those uh, calculators. So we use the one of the famous online calculators, what they call Desmas. So if you use the Desmas calculator, online calculator, you can find that on this website, and this is the link for this graph. And if you use this link, you can see you're gonna reproduce this graph, and you can see this is what you get as the graph if you use them like a larger scale. And we didn't use much larger scale here, so we this was like kind of close to what we get, but this is what you get if you use larger scale, especially for -20 to 25. And for the y coordinate, y-axis, we use actually -15 to +15, so it's a larger scale. So you actually see the graph there. Okay, so that's the graph of the first one. So let's look at the second problem. So we have y equal 3x squared minus 6x divided by x squared plus x minus 6. Again, we're going to go with the factorization first. You can see 3x is a common factor. So you're going to get x minus 2. And from the bottom, you can see it is positive 3, negative 2. So x x positive 3 and x negative 2. Okay, good. So that's the factorization, and also we can look at the simplified version. So it is 3x over x plus 3 after you cancel the common factor. So let's go step by step again. So we already had the factorization, so that was done, and then we're gonna go for the domain. So domain coming from the unsimplified version. So we're gonna look at this version. So there are two zeros. So x not equal to -3 and x not equal to 2. So if you use those two values, then the domain is x such that x are not equal to -3 and x not equal to 2. Those are two values you get. And then we're gonna go with the asymptote intercept. So y-intercept. So y-intercept means you plug in x equals 0. So if you plug x equals 0, you get 0 over -6, which is 0. And then also we're going to go with the x-intercept. So the x-intercepts are to find the x-intercept, you have to look for the simplified version. The reason is in the unsimplified version, x equal to is not in the domain, so you can plug in the value. So that means, so you remove x minus 2, so you look at the simplified version. In the simplified version, we have 3x, so we're going to set 3x equal to 0, and this gonna give you x equals 0. So that is the only x-intercepts we have. And then the next step is asymptote. So we're gonna go with the vertical asymptote first. So the vertical asymptote is coming from the simplified version. So if you look at the simplified version, you can see x plus 3. So that means x equal -3 is a actually is the, you can say, is the only vertical asymptote. The other factor get cancelled out, so it doesn't produce asymptotes. Okay, now what we can do, we can look at the sign diagram after we get the asymptote. So let's put zeros and the vertical asymptote. So we have 1 0 and 1 vertical asymptote, so we have -3 and 0. So we're going to mark the vertical asymptote, and then we're going to pick zeros around and in between zeros and vertical asymptote. So that means the value would be, you can pick a value like t equal -2. So you get negative and positive. So you can plug into any version. So we can plug into the simplified version. So you're going to get those two, that means negative. And then we're going to plug in t equal -4 this side. So you plug in -4, which is negative over negative. So 2 negative means positive. So that's what you get. So that means the graph gonna go to -infinity on this side and +infinity on that side. Okay, so we have the information we need. Now we're gonna find the horizontal asymptote. So to find the horizontal asymptote, we're gonna check the degrees of the numerator and denominator. You can see it's m equal 2, so they are the same. That means as before, the ratio gonna give you the asymptote an over bm, so that means 3 over 1, so which is 3 is a horizontal asymptote. Good, so we have a horizontal asymptote, and then the last thing what we can do, we can check whether the graph gonna cross the horizontal asymptote. So check whether the graph crosses, or you can say meets the horizontal asymptote. For that, what we can do, we can set them equal. So we have 3x squared minus 6x over x squared plus x minus 6. And we set this equal to 3. And then if you cross multiply, you get 3x squared minus 6x. From the other side, you get 3x squared plus 3x minus 18. And you can see these get cancelled out. So you get -9x equal -18. So in other words, x equal 2. So at x equal 2, the graph gonna actually x equal 2 is not in the domain. So that means that is the time as the graph gonna meets the horizontal asymptote. So now let's see how the graph gonna looks like. So we're gonna graph the function now. Again, we can start with the axis. So we have the x-axis and the y-axis. So we have, and then we can mark the 0. So that is 0. And then also we have 2. At 2, there's a 2 is one of the values at which the graph gonna cross the asymptote, and then -3 was the only vertical asymptote. That's the vertical asymptote. So this is x equal -3, and then also there was the we had the horizontal asymptote, that's also 3. So we have this one. So this is y equal 3, so that is the horizontal asymptote. So this value is 3, and then we also know that the graph gonna grow like this in the bottom and like this in the top. So we can use those information to finalize the graph. That means this side you can graph, so it's gonna go like this. And then we also know that at 2, the graph gonna meet the horizontal asymptote, but at 2 the is open because 2 is not in the domain. That means there should be like a hole in there because that point is not in the domain. So now we can, and then 0 at 0, that's one of the x-intercepts. So the y-intercept is also 0. That means graph gonna pass through that. So we're gonna use that information here. So that means if you connect the dots, so you're gonna get the graph is gonna pass through this point and gonna go there. And then what happened here is gonna go up now, and then it's gonna go down. So there's a local maximum, but unfortunately using pre-calculus we cannot find the local maximum for that we need calculus. So that is the final graph you're gonna get. So there's a hole in there at 2 because 2 is not in the domain of this function. So this is the final graph you're gonna get. So unfortunately the graph given at the decimals is not correct. So the graph given by the decimals is not correct. So you can try to find it, and you can see I get a wrong graph. One of the reason is 2 is not in the domain because you're dividing by 0 if you include that point. Yeah. So that's the mistake there. So that's not accurate. Okay, good. So let's go to the last problem of this type. So we have y equal x squared minus 3x minus 4 divided by x plus 2. Again, as the first step, what we always do, we can look at the factorization. So it is x minus 4, x plus 1 divided by x plus 2. And then 2 says that x cannot be equal to -2. Okay, good. So, and then if you look at the steps, so it's a factoring is done. So we're going to go for the domain. So the domain is x such that, so you can see x such that x not equal to -2, and then the intercept, so the y-intercept. So the y-intercept is plug in x equals 0. If you plug in x equals 0, you get y equal -4 divided by 2. So you just need these two numbers. So that means you get -2. And the x-intercept, so you look for the simplified version, and this is already the simplified version. That means you're gonna set that the product, the numerator equal to 0. So if you set the numerator equal to 0, you're gonna get the two values x equal -1 and 4. So those are the two zeros we have, -1 and 4. And then the next one is we're gonna go with the vertical asymptote. The vertical asymptote is coming from the denominator, so that means x equal -2 is a vertical asymptote. After we get the vertical asymptote, we look at the sign diagram. So let's look at the sign diagram again. For the sign diagram, we put zeros and the vertical asymptotes only. So we have -2, which is a vertical asymptote. That's a vertical asymptote at that point, and then we have -1 and 4 as zeros. So we're gonna check the sign around the vertical asymptote and between zeros. So that means we only need to check two this time. So we're gonna plug in a value like t equal -1.5. So if you plug in t equal -1.5 into factors, you're gonna get negative, and then positive. So those are the factors you get. That means 2 negative, that means this is positive. So that means at this corner the graph gonna go like that. And on the other side we have t equal -3. So if you plug in -3, you can see that it's negative, and also another negative. So 3 negative, that means negative. That means graph gonna go to -infinity on this side. So we know the behavior, and we also know the two zeros. So next thing is we can look at the horizontal asymptote, and you can see that in this case there are no horizontal asymptote because the two numbers doesn't match. So let's go with the horizontal asymptote. So you're gonna say no. Okay, there are no. horizontal asymptote, no horizontal asymptote. But you can see here n equal 2 and m equal 1. That means n is exactly m plus 1. So according to theory, so what should happen? There is an oblique asymptote. There is an oblique asymptote. So to find that, we can use the division, either log division or the synthetic division. So just for this example, I'm going to do this log division. So we can divide the two polynomials. So we have x squared minus 3x minus 4, and then divided by x plus 2. You can see that the x is missing. So if you multiply by x, you get x squared plus 2x. You're going to subtract. Subtract means change the sign of the bottom one and add. You get negative 5x. I move the negative 4 down. So the missing number is negative 5. So once you multiply by negative 5, so negative 5x and negative 10. Again, change the sign and add. You get 6. So this is the quotient, and that's going to give you the oblique asymptote. So you can see y equal x minus 5 is an oblique asymptote. Okay. So and then what we're gonna do is we also need to check whether the graph gonna cross the asymptote. So let's check that now. So we're gonna check whether graph crosses the asymptote. So for that, again, as before, we're going to set the two equal. So we have x squared minus 3x minus 4 divided by x plus 2. That's the function. We're going to set this equal to the asymptote. In this case, is x minus 5. That's what you get. And then if you cross multiply, you get x squared minus 3x minus 4. And then this side, you're going to look at the product of these two. So which is x squared minus 3x minus 10. And something interesting happen. You can see x squared get cancelled. Negative 3x get cancelled. So you get a negative 4 equal negative 10. And this is a contradiction. This is not possible. Okay, not possible. Not possible means that the graph does not cross the asymptote. Okay, so it's not possible means the graph does not cross. Okay, so you can say does not cross. Okay, that's the idea, because you get something impossible if you try to do that, so it's not going to work. Okay, so we have all the information we need. Now we can graph the function using those information. So again, we're going to look at the we're going to draw the axis, so x-axis, and then the y-axis. And then the next thing is we're gonna also graph the asymptote. So you can see in this case the asymptote is y equal negative 5. So so the asymptote is y equal x minus 5. So which is a slope, one slope and negative 5 intercept. So that means you can draw it like this. So that's the asymptote. So this is negative 5. And also we have this vertical asymptote at negative 2. So this is 5. And we also have vertical asymptote at negative 2. Okay, so this is negative 2. So this is x equal negative 2. And then we can mark the other information we have. So we know that there was a 0 at negative 1, and there was also another 0 at 4. So these are some of the information we had. This is 4 and this is negative 1. Good. Okay, and then also we know that the graph gonna go to infinity in this corner and negative infinity on that corner. So that means since these two are asymptotes, so we can graph this side like this. So it's gonna go like that. And then also this is asymptote for the right side. So that's going to continue, and then this is one of the zero. It's passed through this zero and pass through the other zero, and it's gonna continue, and that's the asymptote. Okay, that's the shape of the graph. Um, and we also know the intercept. There's an y-intercept which is -2. Okay, so that is the graph we're gonna get, and we can look at if you use the Decimus what kind of graph we're gonna get, but it should be close to something like this, and then you can see the slant asymptote here. So that's a slant asymptote. Uh, and then so this is the graph you're gonna get. So let's see y-axis and the x-axis. Okay, so let's see what the Decimus gonna give us. So if you use the Decimus website, and you can see this is the graph we're gonna get for this problem, and you can find the URL for this one, and if you use this URL, you can see the graph there. Okay, so let's go to the next problem. In this problem, we're gonna solve several inequalities. So there are two polynomial inequalities, and there are four rational inequalities. So when we have a general polynomial rational inequality, so there are there are three methods to solve the problem. So first one is the algebraic method. The second one is the what we call the sign diagram method. Method. So the third one is the graphical method. So out of those three, we're going to use a sign diagram method because that's the easiest. Because you know that the algebra method is really long, and then so sign diagram method is the shortest and is easiest. And graphical method we normally don't use much because of its time consuming. Okay, so let's look at the first problem. So we have x minus 1 times x plus 3 to the cube less than or equal 0. So if you get a problem like that, what we normally do factoring. So that is already factored. And then what we next what we can do is we can look for the zeros. So what are the zeros here? So you can see x equal 1 and x equal -3 are the zeros. And then we're going to go for the sign diagram. So sign diagram. So for the sign diagram, we're going to first mark those zeros in the order smaller to larger. So we have -3 and 1. Now what we're going to do, we're going to pick a test point. So we're going to pick a test point like t equal 2 and plug in that value into the inequality to the factored version. So you can see when you plug in t equal 2 to the first one, you get 2 minus 1, which is 1, which is positive. So you can say plus a positive sign. And then when you plug in t equal 2 to the second one is 5 cube, which is still positive. So positive means positive. So you get a positive sign. And then we're going to pick t equals 0 as the test point in between -3 and 1. And if you plug in 0, you get -1, which is negative. If you plug in t equals 0 for the second one, which is positive, so negative positive means negative. And then here we're going to plug in t equal -4. If you plug in t equal -4 the first one, which is negative. If you plug in t equal negative for the second one, which going to give you -1. -1 cube, that means odd power, which is negative. So negative means positive. So that's what you get as the sign. And then we're going to pick the one we need. So according to inequality, we're looking for wherever it's negative. So that means it's negative in this middle interval. So that means the solution is, which is going from -3, and you can see it's less than or equal. Since there's the equal sign, the endpoints are included. You can see the endpoints are included. So that means it is -3 to 1 including. So that is the answer, and you can see it's not that difficult. So this is how you solve a inequality like that. So let's go to the next problem. As the next problem, we have -2 times 1 minus x cube, x plus 2 to the 6 greater than 0. Again, we're going to follow the same argument. We're going to go with the factoring. But if you get a problem like that, actually there's another method. You can first divide by -2, and then once you divide by -2, you're going to switch the inequality, and then we're going to work with that. But here I'm going to just use the one as it is and see how it's going to work. So first step is always factor. That's already done. So we're going to go with the zeros. So the zeros are x equal 1 and -2. And then we're going to go with the those are two zeros, 1 and -2, and then we're going to go with the sign diagram. So sign diagram. So we again mark the two zeros. So the two zeros are one is -2, so the other one is 1, and then we can again pick the test point as before. So we're going to pick t equal 2. So when you plug in t equal 2, the -2 is going to give you a negative sign. And then the first factor, when you plug in t equal 2, you can see 1 minus 2, which is -1. It's a negative number. When you raise to 3 times, it's still negative. And the second one is always positive because of even power. So that's what you get. So 2 negative and 1 positive, that means positive. And then we're going to plug in t equals 0. If you plug in t equals 0, it's again negative. And then the first factor, which is positive, and the second factor, which is always positive. So there are 1 negative, that means negative. And then we're going to plug in t equals -3. So you plug in -3, first one is negative, and the second one is when you plug in -3, 1 minus x becomes 4, which is positive, and then last one is always positive. So there are 1 negative, so that means it is negative. So what you notice is if there's an even factor, if there's an even power, even multiplicity around the 0, in this case 0 is -2, you can see around the 0 they have the same sign. So that's something you can see. So if you have an even power, around the corresponding 0 is the same sign, either positive or negative. So that you can notice. Okay, so and then we are looking for where this is positive. So you can see it's positive only on this one. So and then you can see this is strict inequality. There's no equal sign, so that means you cannot include the boundary points. That means at 1 it is open. So the solution is 1 to infinity. Good. So and then also, if like this is the extra one, if you had the inequality -2, 1 minus x cube, x plus 2 to the 6th power less than instead of greater than, then it's going to be the other two, but you can still see that you cannot include -2 in the solution, because if you put -2, it's going to be 0. That means you have to remove -2. So that means if this is the case, the solution is, for this one, the solution is -infinity to -2 open, and then -2 to 1 open. So that's what you get as the solution if you had the other way. Okay, so this is one way. The second method is I'm going to call this the other method. So let's say what else we can do. So if you had the problem like -2, 1 minus x cube, x plus 2 to the 6th power greater than. So what you can do is first you can divide by this number. If you divide by this number, what's going to happen is going to switch the inequality. So you get 1 minus x to the cube, and then x plus 2 to the 6th is going to be negative. You're going to switch the inequality. So this problem is very similar to the first problem, and then you can solve it. And also there's one more thing, and you can see that when there's an even power, this factor is always positive or 0. So that means this is greater than or equal 0. So that means it's since this is positive, you can ignore this when you in the sign diagram, because this is always a positive term or 0. So we can ignore that when you find the sign in the sign diagram. So that's something you can use. So that means you can simply consider 1 minus x to the cube negative for the sign diagram. And also need to focus on the boundary points. So focus on the boundary points. Focus on the boundary points. Okay, so let's look at the next problem. So as the next problem, we have x minus 1 divided by x squared plus 4x minus 3 greater than or equal 0. And this is a rational inequality. So this is not a polynomial inequality. This is a rational inequality. So we can use the same argument because it doesn't matter whether it's a polynomial or rational, except we can avoid dividing by 0. So otherwise it's just similar to solving a polynomial inequality. So we're gonna go follow the same path. So we're gonna go with the factoring. So that's the first step. So if you factor, you can see that you're gonna get x minus 1 from the top. From the bottom, you're gonna get x plus 3. You can see x plus 3 and x plus 1. Actually this is positive, so it is x plus 3 and x plus 1, so greater than or equal 0. And again so we factor this. Now we're going to go with the zeros. So the zeros are, so we have 3 zeros actually. There's a 0 from the numerator, which is 1, and then negative 1 from the bottom, and then negative 3 also from the bottom. And then we're going to go with the sign diagram. So we're going to go with the sign diagram. So we're going to put the zeros in that order. So and then the zeros are negative 3, negative 1 and 1. And then we're going to pick the test points. So it doesn't matter where the zeros coming from, you just put the zeros there. And then we're going to pick the test points. So t equal to is a good test point. So if you plug in t equal to from the top, you get positive, and from the bottom first you get positive, from the other one you also get positive. So 3 positive means positive. And also there's a shortcut. If the factors have odd powers, in this case each multiplicity is 1, that means they are odd. So what's going to happen in the sign diagram is going to switch the sign. That means we only need to find the first one, so the next one should be minus, plus, minus. When these multiplicities are odd, it's going to switch the sign like that. And we can verify that whether that's the case. For example, if you plug in t equal 0, you can see you get negative, and then you get positive, so that means negative. And then good number here is t equal negative 2. If you plug in negative 2, you can see it is negative, and then positive, and then negative. So the 2 negative, which is positive, and then you can plug in t equal negative 4. So you plug in negative 4, you can see which is negative, and then negative and negative. So 3 negative means negative. So now we can write the solution, but you have to be careful. You want to make sure that you're going to remove the zeros from the denominator, because to avoid dividing by 0. So that means we're going to remove negative 3 from the solution, and we also remove negative 1 from the solution, because those are the zeros in the denominator. So and then we need wherever it's positive, so that means one is this and the other one is that. So now we can write the solution. So the solution is the solution is, so it is negative 3 comma negative 1, both open, and then union, and then 1 is closed, 1 to infinity, because 1 is coming from the numerator. So that is the solution for that problem. So let's go to the next one. So as the next problem, we have x minus 2 divided by x plus 1 less than or equal 3. And you can see that this problem you have numbers on the both sides. So when you see numbers on the both sides, what you want to do is to bring the numbers to only one side. So we're going to bring everything to the left side. So we can write this one as x minus 2 over x plus 1 minus 3 less than or equal 0. And then we try to take the common denominator. So so you can just cross multiply to get that, or you can see here x plus 1 is missing, so you can multiply by x plus 1 to the top and bottom, and then you can see it's a common denominator now. So once you take the common denominator, you're going to get x minus 2 minus 3x minus 3 from the numerator. From the denominator it is x plus 1. This kind of simplifies to negative 2x, negative 5 divided by x plus 1. And then what you can do is you can make it more simpler. You can divide by a negative sign. When you divide negative sign, you're gonna get simply 2x plus 5 divided by x plus 1, and you can switch the sign. So, and after we come to this level, and you can see this is a very simple problem, like as we did before. So we're gonna use the same argument now. So that means this is what you need to do. So that means if you see numbers on both sides, bring it to one side and simplify, and then look for the complete factored version. So this is a complete factored version, and after that all those problems will be very similar. So and then so what we normally do is so is a factoring, so we did it, and then we're gonna go for the zeros as before. So the zeros are, so to find the zeros, we have 2x plus 5 equals 0, and the bottom x plus 1 equals 0, and then this is gonna give you x equal negative 5 half, or x equal negative 1, and then we draw the sign diagram. So we're going to put these two numbers from smaller to larger. So this is negative 5 half and the negative 1, and then you can pick test points. You can pick t equal negative you can pick t equals 0, that's the easiest number. So if you put t equals 0, and if you plug in, you get positive and positive from the two, so that means positive. And then t equal, you can also use a shortcut because these are all have odd multiplicity. That means this there should be sign switching signs, and you can also see that if you plug in negative 2, this is positive, and the bottom one is negative, so this is negative. And if you plug in t equal negative 3, you can see first one is negative and the bottom one is also negative, so it is positive. You see the sign change from plus minus plus. Okay, so and then we are looking for wherever it is possible, and also don't forget to remove zeros from the denominator. Then you can remove negative 1 because that's a zero of the denominator. So now we are looking for where it is positive, that means this and that. So those are the answers. So we can write the solution. So the solution is it is negative infinity to negative 5 half, including, because that's equal sign and it's in the numerator, and then the union negative 1 to infinity. We remove negative 1 because that's coming from the denominator, even though there's equal sign, because to avoid dividing by 0. Okay, so let's go to the next problem. As a next problem, we have negative 5 times 3 minus x to the cube, 2x plus 1, x squared minus 25 are less than 0. So what we can do, and we see that there's a number like negative number. Since you have a negative number, we're gonna divide by that. So so dividing by negative 5, you're gonna get 3 minus x to the cube 2x plus 1 divided by, and then also we can factor the denominator. So you have x minus 5 and x plus 5, and then since it's we divide by a negative number, it's going to switch the sign, so it's going to be positive now. Okay, and then here we use the x squared minus y squared equal x minus y, x plus y factoring. Okay, this is the differential squares formula here. Okay, good. Now we have, this is the complete factored version. So we're gonna so the factoring is done. So the factoring is done. So we're gonna go with the zeros. So the zeros are, so we have 3 from the numerator and negative 1/2 from the numerator, and then plus or minus 5 from the denominator. So we're gonna put all those 4 numbers in the number line. From smaller to the larger, so we're going to start with negative 5, that's the smallest, and then negative 1/2, and then 3, and then 5. So those are the numbers in that order. So we're going to go with the test point, and you can also see that everyone has a odd multiplicity. Each factor has odd multiplicity. That means we can, in the shortcut, we only need to find the sign of one of them, one region, and then the other we can switch the sign. Good. So let's do that. So we're gonna pick the t equals 6 as a test point. So if you pick t equals 6 from the first factor, if you plug in t equals 6 in the first factor, is a 3 minus 6, which is negative 3, which is negative, odd power, so it is negative. And then the second factor is positive, and then 6 minus 5, which is 1, so positive, and then positive. So we have one negative sign, so it is negative. And then since all the multiplices are odd, there should be a sign change. So that should be the sign change. And you can also check this by plugging some values. For example, if you plug in t equal 4, you're gonna get minus, plus, and then minus, plus, and if you plug in t equals 0, you're gonna get plus, plus, and then minus, plus, and then if you plug in t equal, you can say negative 1, so you're gonna get plus, minus, so it's not minus 1, so we say just say minus, and then minus, and then plus, and then t equal negative 6. If you plug in negative 6, you can see this is plus, minus, minus, and minus. So you can see this can give you the signs already marked there. Good. And then we also need to remove the zeros from the denominator. So that means we can remove negative 5 and 5 from the answers. So we are looking for wherever the product, the ratio and the product are positive, so that means this and that. So those are the solutions. So then we can write the solution as, so the solution is, so open at negative 5, close at negative 1/2. Actually, it is open at negative 1/2 because there's no equal sign. So this has to be also open, and then union, and then we have 3 to 5 both open. 3 to 5 both open. So that is the solution for this problem. So it's not long, and you can see it's very short problem. Sign diagram helps you for to find the solutions. So let's go to the last one. So we have this one. So we have x over x plus 1 greater than or equal 2 over x plus 3. So you can see there are terms on the both sides, so we're going to bring it to one side. So it is x over x plus 1 minus 2 over x plus 3 greater than or equal 0. Now what we can do, we can simplify this, and we're going to use the cross multiplication when we have different denominators. So that means we can write this one as x plus 3 minus 2x plus 1 divided by x plus 1 over x plus 3 greater than or equal 0. and then we're going to simplify the numerator. When you simplify the numerator, you're going to get x squared, and then we have 3x minus 2x, so x, and then negative 2 divided by x plus 1, x plus 3 greater than or equal to 0. So this is very close to the problem that we did earlier. So we're going to factor the numerator now. So when you factor the numerator, you're going to get x plus 2 x minus 1 divided by x plus 1 x plus 3. So we're going to look for all the zeros, and then the zeros are, so you can see we have x equals negative 2, 1, negative 1, and negative 3. So then we're going to put those zeros in a number line and check the sign. So we can put them in a number line from a smaller to larger. So we have a negative 3, negative 2, a negative 1, and 1. So we're gonna pick a test point, and you can see that all the zeros have multiplicity 1, which is an odd multiplicity. That means we only need to find one number. So we're gonna pick t equal 2. We plug in t equal 2 in the first one, you get 4, which is positive, and the second one you get 1, which is also positive. From the bottom, the first one you're gonna get 3, so which is positive, and the second one from the bottom 5, which is positive. So 4 positive, that means positive. Since the odd multiplicity, you're gonna switch the sign. So that's what you get. That's a sign diagram. And also we're gonna remove the zeros from the denominator. So negative 3 is one zero from the denominator, negative 1 is another zero from the denominator. And then now we are looking for where the inequality is positive. So that means you're gonna look for these three regions, 1, 2, and 3, and excluding the zeros from the denominator. So you can write the solution as, so the solution is going from negative infinity to negative 3 open, and then union, and then we have negative 2. Actually negative 2 is 0 in the numerator, so we can include that. So it's a negative 2 to negative 1 is again from the denominator, so you exclude that, and the union, and then we have 1. So so 1 is a 0 from the numerator, so we can include 1, and to infinity. So that is the answer for this problem. In this problem, we can learn about the composition. So that means when you have f circle gx is defined as f of gx, so that is the definition we're gonna use. So that means we're gonna substitute gx into the f function. That's what we normally call the composition. So we use the definition for all these problems. So let's start with the first one. So what is saying that so you are given two functions f and g, and then you need to find these four things. So let's go one by one. So let's look at the first problem. So we have fx equal to x cubed minus x plus 1 and gx equal 1 minus 4x. So the first thing we're gonna do, we're gonna find what are the corresponding domains. So the first, these two are both polynomials, so the domain is all real numbers for both of the functions. So all real numbers. And then we're gonna go to the first one, asking what is f of g a negative 1. So if circle g a negative 1. So if you look at the definition, this means that f of g negative 1. So what you're gonna do is we're gonna find this first. So g to the negative 1. That means go to the g function and plug in negative 1. So if you plug in negative 1 in the g function, you can see that you get 5. So that means this is so g negative 1 is 5, and then this means that you need to plug in 5 into the f function. So go to the f function and plug in 5. So 2 which is 5 cubed minus 5 plus 1. So if you simplify, you're gonna get 246. And then part 2, in part 2, what we're going to do is we're going to find G circle fx. Um, Again, we use the definition. According to the definition, this is G of fx. That means we're going to substitute fx function into the G function. So the G function is 1 minus 4x, so that means 1 minus 4. You can replace x by the G function, which is 2x3 minus x plus 1. And also you can simplify this. If you simplify, you're going to get negative 8x cubed, and then you're going to get 4x, and then you're going to get 1 minus 4, that means negative 3. So that is the G circle f function. And the next one is we're gonna find f of f actually f of 0. So that means if you look at the definition again, this means that f of 0. So we're gonna go the innermost function. So that means we're going to calculate this first. That means go to the f function and plug in 0. So that means when you plug in 0 to the f function, and you're going to get 1. So we have f of 1 now. Now what we can do, go to the f function again and plug in 1. So if you plug in 1 to the f function, so you're going to get 2 minus 1 plus 1. That means f2. Now we plug in 2 to the f function. If you plug in 2 to the f function, is 2 to the cube minus 2 plus 1. If you simplify, you should get 15. Good. And then for the last part, what we have is we're going to find several domains. So what you can see that the since f and g are polynomials, and we know that the domain of f equal domain of g equal all real numbers. So that means you can plug in any value there. So that because of that, the domain of f circle g equal domain of g circle f equal all real numbers. Good. So let's look at the next problem. So in the next problem we have fx equal x minus 3 square root, and the g function gx, which is 1 minus 4x. So we did not change the second function. And first we can look at the domain of these two functions. The domain of f, we want to make sure that whatever we plug in has are gonna create something positive because with a square root. So that means you can plug in 3 or more. So that means the domain is simply 3 to infinity, and the domain of f, because this domain of g, since this is a polynomial, is all real numbers. So those are the two domains of the two functions. So let's start finding one by one. So we're going to start first one, which says that f circle g negative 1. Again, we use the definition, which is g or f of g negative 1. That means we're going to find g negative 1 first. That means go to the g function, plug in negative 1, which is 5. And then go to the f function, plug in 5. So that means 5 minus 3 square root, which is square root 2. Okay, so let's go to the next part. So part 2. In part 2, we're going to find g circle f x. So that means by the definition, this is g of fx. That means you're going to plug in fx to the g function. So if you do that, it is 1 minus 4. You can replace x by the fx function. So that means it's x minus 3 square root. So that is a g of fx. And then the next one is we're going to find f of 0. So what this means is you're going to plug in 0 to the f function. So it is f of 0. So but you can see that you cannot plug in 0 to the function because it's with 3 or more. So that means the inner function not defined. So since the inner function is not defined, the whole function is not defined. So not defined since f0 is not defined. Okay, because the inner function is not defined, so that's the whole function not defined. Okay, so let's go to the part 4, which is f circle g. So you can find the domain of f circle gx. So let's look at the definition, which is f of gx. So what need to happen is we know that in the f function, so the domain is 3 to infinity. That means it should be 3 or more. So that means whatever come out as the output of the gx function has to be 3 or more. So we can use that argument here. That means 1 minus 4x has to be 3 or more. Now we're gonna solve this inequality. We know how to solve this inequality, so we're gonna bring 1 to the other side and then divide by negative. When you divide by negative, it's gonna switch the sign. So this is gonna give you negative 1/2. So that means x is anything less than or equal negative 1/2. So that means the domain of f circle G is negative infinity to negative 1/2 including. Okay. And then since the G is a polynomial, that means you can plug in anything there. So that means we can use this argument because we know that the G circle fx is equal to G of fx. But since G is a polynomial, what you can say is the domain of G circle f is simply the domain of f, because you can plug anything into the G function. That means it is from 3 to infinity. That's the domain of that. Okay, so let's go to the next problem. So we have t equal 4 divided by t minus 3 and gd equal 2 divided by t plus 5. So we can avoid dividing by 0. So that means the domain of f has to be anything that doesn't make the denominator 0. That means t cannot be 3. And then for the g function, you can see that t such that t cannot be negative 5. So those are the two domains. So the first part, so we can say f circle G negative 1. So that means f of G negative 1. So go to the G function and plug in negative 1. So it is f. So go to G function, plug in negative 1, it is 2 over negative 1 plus 5. So that means which is f of 1/2. So now what we can do, go to the f function and plug in 1/2. So what happens is a 4 divided by 1/2 minus 3. Now we're gonna simplify this. So it is 4 divided by negative 5/2. And then when you multiply by 2 both sides, you're gonna get negative 8/5. Okay. And number two, G circle fx. So which is G of fx by the definition. So go to the G function and plug in fx, which is 4 over x minus 3. So we change the variable because you need the function x, not t. Good. And then so if you plug into the G function, which is 2, you replace t by 4 over x minus 3 plus 5. Now the question is how to simplify this one. So the goal is to simplify this. So to simplify this, we can multiply the top and bottom by this denominator. Once you multiply by that denominator, that get cancelled from the first term. So you're gonna get 2 times x minus 3, and in the bottom you get 4 because the denominator get cancelled, and here you get 5 times x minus 3. That's what you get. Now what we need to do is simplify. So this is easy to simplify. You get 2x minus 6, and in the bottom you get 5x, and then we have 4 and then minus 15, so which is negative 11. So that is the G circle fx. Good. So let's go to part 3. So in the part 3, what we're trying to do, which is f of 0. So by the definition, this is f of f0. So that means plugging 0 to the function, f function. So that means it is f of if when you plug in 0, you get negative 4/3 from the f function. Now what we can do, we're going to plug in negative 4/3 to the f function. So that means which is f of, you plug into the f function, which is 4 over negative 4/3 minus 3. So this one is easy to simplify. You get 4. Again, we can multiply by 3 the top and bottom. When you multiply by 3 as before, you get 12, and then negative 4 and negative 9. So this one you can simplify to negative 12 over 13. So we're going to plug in that value into the function again. So that means it is 4 over negative 12 over 13, negative 3. And then you can multiply by 13 the top and bottom. So you're going to get negative 4 times 13. From the bottom you get 12. And then plus 39 when you multiply, or you can write it like that, then you can see what you did. Now you just need to simplify. It's a negative pull out, and then 52, and then you get 12 plus 39. You can see this is simply negative 52 over 51. Okay, so so the last part of that problem is, so we have f circle G T, so which is f of GT. So what you want to do is, now we have like a rational function, so you have to be careful what kind of domain we have. So the first we notice that, so you can say, so first t cannot be negative 5, because in the GD function t cannot be negative 5. So that's the first condition from the GD function. And then we also know that because we're going to plug in the GT value to the f function, that means GT has to be in the domain of the f function. That means GT cannot be 3, because we know that the 3 is not in the domain. So that means if the GD output is 3, it's going to create a problem. So that means we're going to use this condition. So GD cannot be 3. Now what we're going to do, we actually set them equal and find for which values GD becomes 3, and then we remove that value from the domain. So that means we set the GT function, which is 2 over t plus 5, equal to 3, to find what value is going to give you that, and then we remove that value. So so that means 2, we're going to cross multiply, so it is 3 times t plus 5. This is going to say 2 equal 3t plus 15, and then this is very easy to solve. You can bring 15 to the other side, become negative 13. So t is negative 13 divided by 3. So from that value the GT becomes 3. That means we have to remove this value. So then we can write the domain as, so the domain of f circle G is, first, so t is any real number which is not equal to negative 5, because it should be in the domain of G. And then also we know that t cannot be negative 13 over 3, because that's going to map to the domain of f, because it should be in the domain. So to avoid, because you know that 3 is not in the domain, so and that value is going to give you 3, so we remove that value. Okay, so that's about that. And then let's try to do the G circle F now. So again, we make a similar argument. So we're going to say, so G circle F X. So by the definition, actually we the variable is t. So so by the definition, this is G of ft. So that means first this should be defined. So again, as before, we can say first the t cannot be 3, and then again ft function should not give you -5, because that value is not in the domain so of G. Again, how we did it, we set them equal and find the corresponding value. So t minus 3, you set it equals -5 and solve as before. So this says that 4 equal -5t is a cross multiplication, and plus 15, and then when you solve, this says that t is -11 over -5. That means 11 over 5. Good. I mean, we have to remove this value, so that the domain of G circle F is any real number such that the t not equal to 3 or t not equal to 11/5. Good. So let's go to the last problem of this one. So which is fx equal square root x, and gx, which is equals to 1 minus x over x plus 3. Again, we can look for the two domains. We have a square root and a rational function. So the two domains are, the domain of f is 0 to infinity, and the domain of g, which is coming from the denominator, it is x such that x not equal to -3. Okay, so those are the two domains. So we're gonna go to the first one. So the first one is f circle g -1. So which is by the definition f of g -1. So we plug in -1 to the g function first. So that means it's a 1 plus 1 over -1 plus 3. So this is f 2 over 2. So 2 over 2 means 1. Now we plug in 1 to the f function, so square root 1, which is 1. Part 2. In part 2, we're going to do G circle fx. Again, by the definition, this is G of fx. So we're going to plug in fx into the gx function, fx into the gx function. So that means square root x. So that means you're going to replace every x in g by square root x. So that means it's going to be 1 minus square root x over square root x plus 3. And you cannot simplify this further, so that's the answer. And part 3. From part 3, we're going to get f of 0. Again, by the definition, this is f of 0. So we're going to plug in 0 to the f function. That's going to give you 0 because the square root x. And again, we're going to plug in 0 to the f function. That's also going to give you 0. And then this going to give you 0. Good. And the last part. So now we have part 4. We're going to find the domain. So first we're going to do f circle gx. So which is by the definition f of gx. So that means we're going to plug in gx function into f. So that means 1 minus x over x plus 3 square root. And then this says that x cannot be negative 3. So now what we're trying to do is, this is called a function. So we want to make sure that uh, the values we're going to plug in into the square function is greater than or equal to 0. And also we want to make sure that you cannot plug in negative 3 into the denominator because it's going to make it 0. So that means our condition going to be 1 minus x divided by x plus 3 greater than or equal to 0. Now what we can do, we're going to solve this rational inequality. So this is a simple rational inequality problem. That's the reason why we did that earlier. Now we know how to do this. We're going to find the zeros. So the zeros are x equal 1 and negative 3. So we're going to put them on a number line. So we have negative 3 and 1. We're going to pick a test point. So the test point, you can put the 2. So if you plug in 2, and then you can see that it's a negative and positive, so it's negative. And we can plug in t equals 0, you get a positive sign. And we're going to plug in t equal negative 4, so negative sign. And then also, because all the zeros have multiplicity, odd multiplicity, so there should be a sign change. And then what we are looking for is the positive region, and also we are going to make sure that we remove negative 3 from the solution set. So that means for the domain of the F circle G has to be negative 3 to 1. You want to include 1 because there's an equal sign, and it's on the numerator. And then we can do the other part. For the other part, that part is actually easy. So it is F, it is a G circle F. This is G circle F X. You know that this is G of Fx. So what we're trying to do, are we going to plug the fx function into the g function? But we know that the fx function is always, this part is always greater than or equal to 0. That means you can simply plug in that value to the g function because in the denominator there's a plus sign. So that means the domain of g circle f is simply the domain of the f function, because there are no restrictions from the g function because you're plugging a positive value. So that means, which is simply 0 to infinity. So that is the end of part 3 of the review.